What specific problem does the SuiteRL method aim to solve in multi-turn collaborative tasks with LLMs?
The SuiteRL method aims to address the challenge of effective credit assignment in multi-turn collaborative tasks involving large language models, LLMs. Traditional reinforcement learning methods struggle with high variance and poor sample efficiency in long-horizon decision-making, particularly in partially observable environments where important information is hidden. SuiteRL improves credit assignments by utilizing training time information that is inaccessible to the actor, allowing a turn-level critic to evaluate actions based on this additional context. This approach enables the model to better leverage the reasoning capabilities of LLMs, leading to enhanced performance in tasks such as back-end programming and front-end design. Ultimately, SuiteRL seeks to optimize the policy for generating token sequences that maximize cumulative rewards throughout the collaborative interaction.
How does the SuiteRL algorithm work? Illustrate the step-by-step methodology, including how the critic and actor interact.
The SuiteRL algorithm operates through a two-stage training procedure designed to enhance credit assignment in multi-turn reinforcement learning tasks. Initially, a turn-wise critic is trained using additional training time information, such as reference solutions, which is not accessible to the actor. This asymmetric structure allows the critic to evaluate the effectiveness of actions based on the hidden information, while the actor only relies on the interaction history. In the second stage, the actor is optimized using the rewards provided by the critic, which assesses the actions taken at each turn. Specifically, the actor generates candidate actions based on the current policy, and these actions are ranked by the learned advantage function, which is trained using preference pairs of trajectories, allowing the actor to improve its decision-making over multiple turns. This methodology results in superior performance in collaborative tasks, as evidenced by the significant gains in success rates compared to other state-of-the-art algorithms.
Can you come up with a simple yet illustrative example on the inner workings of the SuiteRL algorithm? Walk through the main algorithm steps using a hypothetical task.
To illustrate the inner workings of the SuiteRL algorithm, consider a hypothetical task where an agent collaborates with a human simulator to design a web page based on a high-level description. The process begins with the agent receiving the initial instruction and hidden training time information, such as a reference web page. As the agent interacts with the human simulator, it generates HTML snippets and asks clarifying questions to gather more details, leading to a maximum of 10 interaction rounds. During each turn, the agent's actions are evaluated using a turn-wise advantage function, which is trained with access to the training time information, the reference web page, while the agent only sees the interaction history. This asymmetric structure allows the critic to provide more informed feedback on the agent's actions. The advantage function is parameterized using the mean log probability of the actions, and the agent is optimized using the Bradley-Terry objective, which helps in determining which actions are more effective based on the cumulative rewards from the interactions. As the agent iterates through the task, it receives scalar rewards based on the similarity of its final web page to the reference web page, allowing it to learn and improve its performance over time. This structured approach enables SuiteRL to effectively perform credit assignments and enhance the agent's decision-making capabilities in complex, multi-turn collaborative tasks.
What are the theoretical or practical benefits of utilizing SuiteRL over other reinforcement learning algorithms for multi-turn collaborative tasks?
The theoretical benefits of utilizing SuiteRL over other reinforcement learning algorithms for multi-turn collaborative tasks include its ability to leverage additional training time information, which enhances credit assignment for actions taken by the agent. This asymmetric actor-critic structure allows the critic to access hidden training time information, such as reference solutions, while the actor only uses interaction history, leading to improved decision-making. Practically, SuiteRL demonstrates superior performance in experiments, achieving a 6% improvement in success rates for back-end programming and a 4% increase in win rates for front-end design compared to multi-turn DPO. Furthermore, SuiteRL's approach to directly learning the advantage function, rather than relying on a value function, allows for better generalization in reasoning-intensive tasks, as evidenced by its competitive performance against larger models and proprietary systems. Overall, SuiteRL's design choices result in a more effective and efficient training process for LLM agents in complex collaborative environments.
How is the SuiteRL method validated or tested within the context of the Collaborative Agent Benchmark, Kernel Bench? Discuss the experimental setup and evaluation metrics used.
The SuiteRL method is validated within the Collaborative Agent Benchmark, Kernel Bench, through a series of experiments designed to assess its effectiveness in training LLM agents for complex collaborative tasks. The experimental setup involves comparing SuiteRL against various state-of-the-art SOTA, LLMs, and multi-turn reinforcement learning RL algorithms, specifically using LLM-A3. 1-8B instruct as the baseline model. Evaluation metrics include the success rate of tasks in back-end programming, where agents must pass 10 hidden unit tests for each function, and the win rate in front-end design, measured by the cosine similarity of the agent's web page to a reference web page. The results indicate that SuiteRL significantly outperforms other algorithms, achieving a 6% improvement in success rate for back-end programming and a 4% improvement in win rate for front-end design, demonstrating its superior capability in credit assignment and generalization in multi-turn collaborative settings.
What specific results were achieved with the SuiteRL method in comparison to the state-of-the-art algorithms? Highlight the performance improvements observed in practical scenarios.
The SuiteRL method demonstrated significant performance improvements over state-of-the-art SOTA algorithms in multi-turn collaborative tasks on the Collaborative Agent Benchmark, Kernel Bench. Specifically, SuiteRL achieved a 6% absolute increase in success rates for back-end programming tasks and a 4% improvement in win rates for front-end design tasks compared to the multi-turn DPO algorithm. Furthermore, the resulting model using LLM-A3, 1-8B instruct, not only matched the performance of the larger LLM-A3, 1-70B instruct model, but also achieved competitive results against proprietary models like GPT-4o and o1 Mini. In practical scenarios, the success rate for LLM-A3, 1-8B instruct increased from 6.9% to 22.4% when engaging in multi-turn collaborations, showcasing the effectiveness of SuiteRL in enhancing LLM agent performance in artifact creation tasks. Overall, these results highlight SuiteRL's ability to leverage training time information for improved credit assignments, leading to superior generalization and task success.